Hi everyone, hello again, thanks for coming back, and we're ready to move on with our next talk. And our next speaker comes from Germany. Andreas Weis has been writing C++ code in many different domains, such as real-time graphics, distributed applications, and embedded systems. As a library writer by nature, he enjoys writing portable code and exposing complex functionalities through simple, richly typed interfaces. Andreas is also one of the co-creators of the Munich C++ user group, where he shares his passion with others. Currently, he works for Woven Planet, where he focuses on building modern software for safety-critical systems. Deciphering Coroutines, a visual approach. Let's put our hands together for Andreas Weis.
Thank you. Thank you. Yes, so today we're going to talk about coroutines. This is me. You can find me in various places on the web, and in the real world, I'm one of the co-organizers of the Munich C++ user group. I work for Woven Planet, which, if you don't know, it's the software company that was spun out of Toyota, so we focus on automotive software. So why do I want to give this talk? Coroutines are hard. If you have used them in any language, really, then you've probably noticed that they allow for extremely complex transformations of control flow. But in C++ in particular, this is enabled through a feature that has a fairly arcane syntax and changes some of the fundamental rules of the language, which makes the learning curve quite steep when you're first getting into it. What is worse is if you have ever tried to look at C++ 20 coroutines, if you're picking them up, if you have not been using them for a while, if you don't use them in your everyday work, then after a couple of weeks, you will probably have forgotten most of the details again. And then if you want to pick them up again, you have to start from scratch. So they're not only hard to learn, but also hard to remember. And one of the goals of this talk is to not only give an introduction, but give it in a way that you can remember it easily later on when you come back to them. The feature is unfortunately too big to introduce all of it in a single talk. So what I'm going to focus on here for this talk is really the bare essentials of the language mechanism, that is like the syntax and all of the basics for how this works from a language level. This is a very detailed overview, and a lot of what we're going to talk about, if you just want to use coroutines in your project, in particular, if you already have a library that ships with coroutine support, you don't need to actually know most of this. So if this seems overwhelming and overly complicated, then don't be discouraged by that to actually look at projects that do provide coroutine support. In particular, check out Andreas' talk that is in this room right after the break, where he will show the other side of the coin, that is coroutine from a pure user's perspective. And you will notice that a lot of things are a lot easier than what I'm going to show here. So some disclaimer up front. Coroutines are extremely powerful and flexible, but for didactic reasons, I will have to simplify things quite a lot to be able to squeeze it all into one talk. I will keep the explanation streamlined, and please keep in mind that the code that I'm going to show on the slides is very much slide code. So it's meant to illustrate specific relationships in a simplified way, but it should not be taken as advice or best practices for how to write coroutine code in the real world. And then also, as I mentioned before, this is a talk like from a library implementer's perspective, right? The user's perspective is very different. This is if you actually want to start writing your own library that allows your users to use coroutine code, then this is what you need to know. So what is a coroutine? If you've never encountered this before in any language, then think of a coroutine like a function that can be paused in the middle and can then be resumed later on, right? So imagine like your function just executing as normal, and then at one point you reach a suspension point. And then instead of returning control back to the caller and stopping the function altogether, you're pausing the function, right? And now your caller resumes execution, and then at one point later on, it can resume the coroutine, and it will continue execution just where it left off, with all of the surrounding state intact. And this is a concept that takes quite a bit getting used to in the beginning, because it's so different from how we usually reason about functions. One consequence of this design is coroutines are always stateful, because imagine like you need to, when you suspend a function, if you're going to resume it later, you somehow need to save what the surrounding state was when you went into suspension. What was the value that all your local variables had? What was the value of the function arguments that you assigned to it? So unlike a function, a coroutine is always stateful. And one consequence of this is when you call a coroutine for the first time, it looks like a function call. But you should think of this function call really like the call to a factory function that is creating the coroutine state that the actual coroutine will then later execute in. That's a very useful analogy that will help you overcome some of the confusions with coroutines. Another minor detail is that in C++20, the coroutines that we introduced into the language are stackless, which means when you suspend, you always return control to your immediate caller, and you cannot have any functions between that on the call stack that you're also going to suspend. So with that out of the way, let's look at a simple motivating example. This is something that, especially in the C++ community, you see a lot when talking about coroutines. So on the top here, you see a simple function call to an I/O library, and this is a blocking function call, right? You just want to read some data from a socket. The read is going to take some time, and eventually, when it's all completed, it returns you as the return values back the error codes and the number of bytes that were read into the buffer. The problem with these blocking function calls is, of course, you will now spend most of your execution time in this thread waiting for this call to complete, while there's not actually any useful computational work going on. So what you often do instead, if you have an I/O-heavy application, is you're using a library that gives you an asynchronous interface. That is what we see here at the bottom. So the way that these libraries have so far looked like in C++ is typically that you pass them an additional argument, which is a callback, and the async read will just finish right away without giving you any return values. And then at a later point in time, when the read operation is actually completed, it will invoke the callback that you passed there, and the result values, the error code, and the number of bytes read that previously were the return values of the function are now the arguments to the callback. And what that leads to, if you've ever worked with such an API, is this weird inversion of control flow that can be quite challenging to deal with if you're not used to it. You will see lots of this and how this works in detail in Andreas' talk, so please check it out later. What coroutines now allow you to do is to transform the control flow of the asynchronous case to become almost identical to the one in the blocking case. So we still have the situation that when we enter the asynchronous read, that the execution stops at that point, and we don't continue, and we will only be woken up once the results from the operation have become available. But when we're woken up, all of the surrounding state is still intact. So when we're writing this code, we can, for most intents and purposes, just pretend that we would be dealing with a blocking API, which simplifies the code a great deal. So to explain the basics of coroutines, I'm not going to use this example any longer. I'm going to use a much simpler example. And for now, that's going to be generating a range of numbers. I've just picked the Fibonacci numbers here. You can think of any other range of numbers. And I just want a function that generates these numbers, gives them to the user. So the first thing that you might think of, the most simple thing, is to just return a vector that contains all of the numbers. And we heard, if you were in Brandon's talk this morning, like he gave some good arguments why that might actually be the design that you would prefer in a lot of cases. But in some cases, it's not so nice. So one thing that Brandon also mentioned is if you actually don't want to provide the memory for all of the elements up front, then this might not be a good design. Another problem is if you don't know your n parameter up front, right? You might only, while iterating the range, decide whether you need to see more elements or not. Then this is also not a good design. So what we can do instead is what Brandon presented us as the iterator design pattern, which is instead of returning the entire range inside a vector, we're going to return a generator object which has a next member function, and then each successive call to next gives us back the next number from the sequence. And if I now asked you to write such a function in C++, even if you have never heard of coroutines, you are probably able to do this, right? Like something that fulfills this interface, it's not that hard to do. It's not quite as simple as the vector function that we saw before, but it's definitely not too hard either. So I'm using this as an example for coroutines, right? So is this function that we have at the bottom here, is that actually a coroutine? And the answer is, you don't know. Maybe it is. From just looking at the signature, you cannot tell. Whether the function is a coroutine or not is actually an implementation detail of that function. And that's very much a fundamental feature of the mechanism. What that also means is if you want to understand how such a function works, you don't really need to understand too much about coroutines. You really only need to understand the interface of this object that I'm going to return to you. And this object is just a class like any other. Like the example that you see at the top, that will be a perfectly valid full implementation for return type that could be returned from a coroutine. So these are just like classes like any others. So let's look at this weird return type object in a little bit more detail. So as I said in the beginning, the initial call of a coroutine is like a call to a factory function that creates this object which holds all of the state. The interface of this object determines all of the possibilities for interacting with the coroutine, usually. But the fact that what we're calling is actually implemented in terms of a coroutine is an implementation detail. And I don't need to know anything about this as a client. What is also important, since this is just a normal class object, I can do anything in its interface as I can do with a normal class. So it's up to me as the implementer of the function to design what I put in there, what is the interface that I provide to my clients. So now what actually does turn a function into a coroutine? If I can't tell from the function signature, then what determines if a function is a coroutine or just a normal function? And the answer is simply these three keywords. These were added with C++20. If the compiler sees one of these three keywords appear in the body of a function, that makes it a coroutine. And that actually changes quite drastically in places what the rules are for how the body of this function is going to be implemented. So this is what the body of the make-fibo generator could look like if it were implemented as a coroutine. You will notice if you were in Brandon's talk, this is very similar to how generators work in languages like Python. So this function looks almost like the version would look like that just returns the vector. Instead of where we would push back the results into the vector, we now have this co-yield statement. And that basically means that whenever we reach that point, we're going to suspend the coroutine, return the control back to our caller, and give the value that we pass here as a return value back out. So one other thing to notice here is that, like, if you're used to reading C++ code, then a lot about this function does not make any sense. Like, for example, we have this fibo generator return object that we promise to return, but we don't actually have a return statement in the body of this function. Like, nobody ever creates a feature generator here. So, and that's just one example, right? How does this actually work? And in order to understand this better, let's try even more simple to create the smallest possible coroutine that we can think of. So this is the smallest one that I could start with. The body of the function cannot be empty because you need one of the 3 keywords in there to turn it into the coroutine. So let's just have an empty return statement. And now the question is, okay, with a function like this, what does the return type actually need to look like? If I try again the most simple thing that I can think of, I will start off with just an empty struct as the return type. And then the compiler will complain that it is looking for a nested type in there called promise type, which it cannot find. So this is a compiler error that you will get if you try to do this. So yeah, let's try and make the compiler happy and just provide the promise type here as a nested type. And this promise type is now the second player that we need to look at in the coroutine. So why do we need the promise? If you think of the return object as the interface that we give back to the caller of the coroutine to interact with us, the promise type is sort of the counterpart to this that resides inside the coroutine. It is a little bit special in that you will never actually see the promise type appear in the coroutine body because it is an object that is being created for you by the compiler, stored in a magical place, and you can only interact with it indirectly, and we will see how that works soon. It is, however, the main point of interaction between the caller and the coroutine also. It also provides a couple of customization points that allow us to specify what happens at essential points during startup and shutdown of the coroutine. So let's look at this in more detail. Again, if I start out with an empty type for this, the compiler will complain that it's missing some things. The first thing is a getReturnObject function. And this now actually solves the mystery why we didn't see a return statement in the body of the function. Because it's not the body of the function that creates the return object that we hand back to the caller. It's this guy, right? So the compiler will look for this function inside the promise type, and when I call the coroutine for the first time, it will call this function, store the return object that is returned here in a magical place, and then hand that back to the caller of the coroutine when the coroutine goes into suspension for the first time. So this is a little bit strange because it's very different from how we used to think about functions, but that's just how things are. So this is the return type from earlier. The other thing that we need to provide is a function that determines how we handle return from the function. So we can either return a value or we can return void. In my simple example, I return void, so I need to provide the return_void function. You can, if you return a value, have a co-return 42 in your function, then you need to provide the corresponding return_value function. But returning is not the only way how we can leave a function in C++. We could also exit the function through an uncaught exception, and that is what this handler is for. So I also need to provide this. And like for my simple case, I'm just going to leave all of these empty, right? I just want to make my code compile for the moment. Then there's these two guys, initial suspend and final suspend, and they're a bit strange. So those allow me to customize what happens in case of the initial suspend at the very beginning before the coroutine, the body of the coroutine function starts executing, and the final suspend that allows me to execute code right before the coroutine finishes execution. So like if you imagine you're returning from a coroutine with a co-return statement, or you're falling off the end, then after the body has finished executing, the final suspend will execute. And for now, these are just return std suspend always, which is a built-in type for the standard library, and we will see in a second what that does. Because now I can compile this code. This is all the boilerplate that I need to make my simplest coroutine to compile. So I'm going to add a print statement into the body now to like see what's actually happening. And now we'll notice if I execute the coroutine like this, I won't get any message printed to the console. Like main will finish executing, but I won't see the results of the print line statement. And that is because of this suspend always here, because what happens here is the coroutine starts, the getReturnObject function in the promise is executed, everything is set up, but then before I enter the body of the coroutine, I'm going to suspend. I'm going to hit the pause button and hand control back to the main function that was calling me. And since I'm not resuming the coroutine, but I just keep going on, I never see the print statement. If on the other side I say, on the initial suspend, I don't want to suspend, and I do this with this suspend never, then I actually do see the print statement down here. So this is the first example for seeing suspension in action. And to understand a little bit better how this works, we need to look at one more player in the mechanism, and that is the awaitable. So what's the awaitable? If you think back to the beginning, in coroutines, we usually have such a co-await call. And that basically means at this point, I want to hit the pause button. This is where I want to suspend. And you have to give some value as an argument to this call to the operator co-await. The awaitable now is a type that you can co-await on, right? So if you have an object of that type, you can pass that as an argument to the operator co-await, and that will potentially suspend your coroutine function. So if we think back for the motivating example in the beginning, if you have such an async read call, what that will give you back is an awaitable. You can then pass the awaitable to a co-await call, and that will suspend your coroutine, and then the whole mechanism starts executing that will handle the asynchronous execution of this request. The important thing to understand here is an awaitable is an opportunity for suspension. So you may stop executing at that point, but it's not guaranteed. It's actually up to the awaitable to decide whether you suspend or not. It may just decide to continue execution. So let's do the same exercise as before. Let's try to implement this in the simplest possible terms. So the compiler will complain for the empty type that is missing 3 functions. The first one is this bool await ready function, and that tells us whether we actually want to suspend. If we're ready, if we return true here, that means we don't want to suspend. We just continue executing with the coroutine right away. If we return false here, then we actually go into suspension. Control flow is handed back to our caller. The second thing, the await suspend, is the customization point for the code that is executed right before we go to sleep. So if in the await ready we decided, yes, we do want to suspend, then we call await suspend. We get past the handle to the coroutine that is just executing as an argument, and then we go to sleep. And this coroutine handle, think of that like a raw pointer to the surrounding coroutine state that is created by the compiler. We will look at its interface in a minute. The one thing to notice is that you can specialize the coroutine handler on the promise type. If you don't know the promise type, you can use it in a type erased way, but in most cases you actually want to tie to a specific coroutine and give the promise type here, which slightly expands the capabilities of what you can do with it. So that's the same promise type as we had before. And then lastly, we have the await resume function, which is the counterpart. When we do go into suspension, await suspend is executed before we go to sleep. Await resume is executed right before control is handed back to the coroutine when we are resumed again by the caller, right? So coroutine suspends, the caller continues executing, does all kinds of stuff. Eventually, the caller will resume the coroutine, then await resume is called, and only after that, the main body of the coroutine function actually continues executing. And that's all of the awaitable for now. And now we're almost through with all the stuff that we have to look at, which I know is a lot. So the simplest possible awaitable that you could implement is this. You just leave the suspend and resume empty, and on await ready, you just return false. And that is actually this suspend always that we saw before, which is provided by the standard library. And you can probably guess now what the suspend never looks like. Just returns true in the await ready, but is otherwise exactly the same. Lastly, let's have a very brief look at the interface of this coroutine handle. Like I said, think of it as a raw pointer to the coroutine state. It allows us to resume a suspended coroutine, and it allows us to destroy a suspended coroutine. So that is important to know. Those are the two things that you can do. Like if a coroutine has gone to sleep, you can either resume it or destroy it. Both are safe to do. If the coroutine handle is specialized on the promise type, then you also get these two functions which allow you to convert between promise and coroutine handle. So that was a lot. So let's try to write a little cheat sheet to keep track of all of these things. The way that you read this is, if you read it from top to bottom, then basically each line is one step that happens as a coroutine is executed. If you see a slash, that means you either have to provide the left thing or the right thing, right? So for example, here you can just define your own return type, or if for some reason you're not able to give a nested promise type as part of the return type definition, for example, because it could be a primitive type, it could be a type that is not under your control, you can also use the coroutine traits. Then the compiler is going to determine the promise type from your return type, which could just be the nested type. It's going to construct the promise type, and optionally you can give a constructor where the signature matches the signature of the coroutine function, and then you will get passed all of the arguments to the function, also here to the constructor. Then the compiler will call getReturnObject on the promise to get the return object that's handed back to the caller. It will call initialSuspend to give an opportunity for suspension before execution, and then the startup is done. After that, you will enter the body of the function and start executing as you would expect. Similarly, for the shutdown, you either exit by returning a value or by returning void. You could also exit through an unhandled exception. And once the return has been handled, you get the final suspend to, as another opportunity for suspension after the coroutine body has been exited. This is the cheat sheet for the awaitable. This is just the three functions, and hopefully by looking at the names, you can roughly recall what they're doing. So that was a lot of stuff. And I don't expect you to remember all the details of what I've just bombarded you with. The important thing is to remember the rough responsibilities. So the return type is the object that you give back to your caller, the interface that your coroutine provides. The promise type allows you to customize what you do at startup and at shutdown of the coroutine. The awaitable allows you to customize what happens when you actually want to go into suspension, and the coroutine handle is like a raw pointer to the coroutine state. So with all of that in place, let's actually resume a coroutine. So far, the example that we had, we were able to suspend a coroutine, but then we simply never saw anything on the console. So what I want to do now is I want to be able to put a resume call on my return type, and when I call this, the suspended coroutine actually wakes up again, it resumes execution, and I see the message on the console. So how do I do that? Well, the problem that you're probably facing right now is you have all of these different parts floating around, but you don't really understand how they connect. And that's the typical problem with coroutines. So let's try to bring some structure into this. So we know the caller always has access to the return object, right? Because that's the only thing that falls out of the coroutine call. That's the connection there. Similarly, the coroutine always has access to the awaitable, because that's what we call co-await on, right? And the co-await call, that is the main thing that happens in a coroutine that makes it a coroutine. We've also seen that the promise and the coroutine handle are sort of interchangeable because we have these conversion functions that allow us to go from one to the other. So let's try to make this a little less disconnected. So we already know that in order to implement the resume method that we have seen, we somehow need to be able, as the caller, to call the resume function. And the only resume function that we've seen so far is in the coroutine handle. So how can we make that connection? So let's think back of the getReturnObject function that we saw earlier. The getReturnObject is a member function of the promise type. And you can see from the colors that we now have like two players in the same place here, which gives us an opportunity for connecting things. So how about in this getReturnObject function where we create the return type, we actually pass the coroutine handle as an argument to the constructor of the return type that we're going to give back to the user. So remember that the return type, this is something that we write as the author of the coroutine, right? So we can put everything in there that we want. So we just say, yeah, let's just give it a constructor that accepts a coroutine handle as an argument. That's the only thing that's happening here, nothing magical. And then in the implementation for the return type that you see at the bottom, we simply save the coroutine handle to a member variable of that type so that we always have access to it. And now implementing the resume member function on this return type becomes trivial because we simply access our handle member variable and call resume there. And that gives us the connection here. So we add this handle member variable on the return type, and that is now how we can get from the return type to the coroutine handle and eventually to the promise. So that's great, but we still have the right side of the diagram here floating around. So let's see if we can bring that into the picture as well. And here the function that allows us to resolve that is the awaitSuspend function. So if you think back, awaitSuspend, that's the thing that gets called when we co-await something and immediately before the coroutine suspends execution. And this is passed as an argument, the coroutine handle to the surrounding coroutine that is just going to be suspended. And you again see from the colors that we have two things in the same place here. So from the awaitSuspend function in the awaitable, we can actually access the promise. And now everything in our graph is connected. And that is going to be our little cheat sheet now for implementing some simple, essential functionalities with coroutines. So I don't have the time here really to show you any like fancy, complicated examples. So what I'm going to do instead is I'm going to show you two of what I consider the most essential examples for coroutines. And if you understand how those two works, then for all of the more complicated things that you can do, you can basically build them from these essentials. So don't be discouraged if the stuff seems super simple, but this is really the basics. And if you understand that, you can figure out the more complex stuff on your own. So the two examples that I'm going to show is first, how can I pass data from the caller into the coroutine when I wake it up? And how can I pass data from a coroutine that's about to suspend back to my caller, who I'm going to hand control flow to? So let's start with the second one, getting data out of a coroutine. How could this look like? So we're in the coroutine, we have some data that we want to get out. The only thing that we can reach from the coroutine is the awaitable. So let's draft up a simple example like this. We have a coroutine, we want to pass the value 42 out to our caller. The only thing that I can do is have it in the co-await call, hand it to the awaitable. In this case, like the call that you see there, that's simply a constructor call, right? So the answer, that is my awaitable type, and I give it a constructor that accepts the value that I want to pass out. And then inside the constructor, I'm simply going to store that value in a member variable inside my awaitable type. And now the value is in the awaitable, but I have to pass it further down before I can actually get it to the caller. I have to go to the promise. So what I'm going to do next is I'm also going to add a member variable to the promise. And in the awaitSuspend call, which is the connection from the awaitable to the promise, I'm going to use the coroutine handle that is passed to me as an argument to access the promise and then store the value, which I already have stored in the member variable of the awaitable, store that in the member variable of the promise. And now my data lives in the promise. Got it all the way down there. And now the coroutine side is done, right? The await suspend has finished executing. The coroutine has now been put to sleep. And control flow has been returned back to the caller. And now the only question is, how can the caller now retrieve this value that I placed for him here in the promise? So if we look at the diagram, then the path that we have available here is through the return type to the coroutine handle and then eventually to the promise. And implementing this is actually quite straightforward now. Because if you remember, so yeah, this is what the interface is going to look like now. I'm going to call the coroutine. At some point, the coroutine is going to suspend and is going to store the value 42 for me in the promise. Then control is handed back to main, and now main is calling this get answer method to retrieve the value back from the return type. And the way that I implement this is simply remember that we stored the handle to the coroutine as a member variable inside the return type before. So to implement getAnswer, I now simply use the handle to get to the promise through this conversion function, and then access the member variable inside the promise where I stored the value before and hand it back out to the caller. And that's the entire data flow. That is how this direction works. So now let's look at the other side as well. If I want to get data into a coroutine from the caller. So again, the path from the caller side leads through the return object, and like you may notice the pattern, like the promise is where everything connects, right? That's where we always have to get to. So what I want to do is something like this. The coroutine starts executing. At some point, it's going to co-await for data that it needs to be supplied from the outside, right? So I co-await here on this outside answer, and what that means, I'm going to go to sleep now. My caller is going to provide me more data, and once that data is available, I'm going to be woken up again, and then I can continue executing. And the data that was provided to me falls out as a return value of this co-await call when I eventually wake up. And the caller side on the bottom is simply, I'm going to have such a provide function where I put the data in, and then it's going to fall out of the co-await call at the top. So the implementation of the provide function is pretty straightforward. Again, we use the handle member variable that we created earlier on the return type to get to the promise. We again add a member on the promise where we can store the value. We write it to there, and then we just resume our coroutine. You could also decouple the providing of the result and the resumption, put them into two separate functions, but for simplicity's sake here, it all happens in one function. So now again, the data lives in the promise. So how can the coroutine get to it? Again, the only path is through the awaitable. So what you will see here, if I am going to write now this outside answer awaitable, so I want to return false at await ready, right? I actually want to go to sleep because I need to suspend until the caller has provided me the data that I'm waiting for. In the await suspend, I cannot really do anything because the caller has not executed that, right? I'm still about to go into suspension, so there's nothing that I can do there. So the only thing that I can do here is the coroutine handle, which I get passed as an argument, I store it away so that I have access to it later. And only in the await resume which is executed when the data has been provided and the coroutine is about to wake up again. Only there can I actually access the data. But remember, we stored the data in the promise. And since we saved the coroutine handle before in the await suspend, we can now use that handle to access the promise and get the value back. And now the one thing that we're missing is, like, how do I get the data out of the awaitable and back to the coroutine body? And that happens through the return value of the await resume function. So whatever you return here, that is going to be the return of the overall co-await operator call. That's the connection here. So in our case, since it's a simple int, I'm going to return an int here. And then that is what falls out of the overall co-await expression when the coroutine continues execution. So that's the missing piece here, the await resume function. That is how I can hand the data back out from the awaitable. And that's it. Those are the two ways. Those are the essential use cases. If you can write those, then you can write almost anything. There's one more thing, and that is, if we think back to this example from the beginning. So this is the case, right? We want to pass data out of a coroutine. So we know how to do this using co-await, right? We have to define a new awaitable. I can put the number in there, and then the caller can eventually receive it. But that's a lot of boilerplate, right? What we would like to write is just this. And that, like what you also saw this morning in the Python code, you just want to say co-yield this value. But it's supposed to do this, right? So the co-yield is like a syntactic sugar for a co-await. But I don't want to have to name the awaitable that I'm going to use. And the way that this works is, on the promise type, I have another function which I can optionally provide, which is called yield_value, that takes as an argument the value that I'm going to yield, so the argument to the co-yield expression, and returns as a return value the awaitable that I'm going to co-await on in order to go into to suspension. So with this implementation, that does this transformation for us that we saw in the previous two code examples. But there's one more thing to notice here. You might see that this is a member function on the promise type. So since my eventual goal is to get the value stored in the promise, I can also do this. I just write it to the member value directly, and then just use the suspend always awaitable to just suspend execution. So yield value gives us a shortcut here, right? If I'm going to yield, then in many cases I don't even need to write my own awaitable, can just go straight to the promise, which is quite handy. But with that, the picture is actually complete. So that's a lot of stuff. But the good thing, the good news is that this is really all the syntax that you need. And this shows all of the essential control flow patterns that you need to understand. Again, if you're just going to use coroutines as a library user, you don't need to know most of this. This is really only interesting for library implementers, or like since today, not too many libraries are around. If you want to start playing around with them, you don't have much choice but to start writing your own library. But please feel encouraged to go to Andreas' talk to see like the more simple view from the user side. Believe it or not, but learning the syntax was actually the easy part. It's a lot of stuff to take in, but once you sort of understood it and have played around with it a little, you will see that it's surprisingly mechanical. The challenging part is more how you can actually deal with this asynchronous control flow and use it to make your programs easier. What are some of the interesting problems that you can solve with this, and what are like the algorithms that you would want to use to write such programs? So designing libraries around asynchronous control flow is actually a very deep topic and surprisingly challenging. And I hope we can eventually get to the point where we will be talking more about that than about the comparatively boring technical details of the language feature. For now, I hope that this talk has provided you with everything that you need to pick them up on your own, start playing around with them, get a better feel for that. And I hope that like the little cheat sheet that we created will help you while doing this. So again, this one describing the start and shutdown phase of the coroutines. This one that's describing the awaitable. And finally, this one here, which I think is probably the most valuable one that describes how everything fits together. Here's some references for you if you want to read more. And here you will find a QR code to a PDF that contains all of the parts of the cheat sheet on a simple A4 diagram that you can print out and like put on your desk. And with that, I thank you for your attention.
Andreas Weis, thank you so much.